Hey, it's Zara. In this video, we're going to be talking about this paper, titled A Logical Calculus of the Ideas Immanent in Nervous Activity, published by Warren McCulloch and Walter Pitts in 1943. This is an incredibly important paper. It is effectively the first paper to propose that the human brain can be understood as a mathematical machine, laying the groundwork for both modern computer science and artificial intelligence. But before we get into the math, you need to understand the minds behind it, because their partnership is basically the original Good Will Hunting. Warren McCulloch was a 42-year-old established professor and neuroscientist trying to figure out how the brain processed thought. On the other hand, Walter Pitts was an 18-year-old runaway from Detroit who had been living on the streets, but he had taught himself advanced mathematical logic by hanging out in public libraries. They met at the University of Chicago, combined their expertise in neuroanatomy and symbolic logic, and then later produced this paper. And I honestly found it to be a somewhat difficult paper to read. The central thesis of this paper hinges on biology's all or none law. A neuron either fires an electrical impulse or it remains completely silent. McCulloch and Pitts realized that this mechanism is perfectly equivalent to a logical proposition, being either true, 1, or false, 0. Because of this, they argued that a network of neurons is just a circuit of logical gates. And by wiring these propositions together, the brain can compute complex mathematical and logical expressions. Let's draw this out so you can see exactly how they formalized a biological neuron into math. We're going to establish 5 basic rules based on their physiological assumptions, though we know these are extreme mathematical idealizations rather than accurate representation of modern neurobiology. The first assumption is binary states. The activity of the neuron is an all or none process. So we define ni of t as the state of the neuron I at time t. It equals 1 if it fires and 0 if it doesn't. The second assumption is that of a threshold. A fixed number of excitatory synapses must be active to trigger a firing, and we call this threshold theta. Next is discrete time. The only significant delay in the system is the synaptic delay, the time it takes a signal to cross from one neuron to the next. Time ticks forward in these discrete steps. Next is the veto. An active inhibitory synapse absolutely prevents the neuron from firing at that time, regardless of how much excitation there is. And the fifth is fixed wiring. The structure of the network does not change with time. So again, I want to emphasize that many of these assumptions are not biologically accurate according to our modern understanding. For example, there is no absolute veto inhibitory synapse. It simply provides a negative contribution or relative inhibition, which is something the authors actually discuss later in the paper. However, these assumptions were necessary to write a simple mathematical model. Remember, the whole idea of the paper is to show that if neurons are arranged in certain configuration, they can represent logical propositions. A simple way to write the McCulloch-Pitts firing rule looks like this. The state of the neuron n out at time t is 1, or true, if and only if the total number of firing excitatory synapses at time t-1 is greater than or equal to theta, and the sum of the inhibitory synapses at time t-1 is exactly equal to 0. If these conditions are not met, the neuron does not fire. It's also very important to note that the weights and thresholds in this model of the neuron are fixed, meaning they cannot learn from data like modern neural networks can. Now let's build some basic logic gates using this biological rule we just introduced. So imagine a neuron that fires if it receives a signal from both of its neighbors. This is effectively the AND gate. Neuron 3 receives excitatory inputs from neurons 1 and 2. We set the threshold theta equal to 2. The result is that neuron 3 only fires if neuron 1 and 2 fire at the previous time step. And this is the equation for the AND gate. Both N1 and N2 fire at time t-1 for N3 to fire. Let's look at what just happened here. By simply arranging these idealized neurons and tweaking a threshold, we just built an AND gate. For the authors, this was the ultimate proof of concept. If you could accept their assumptions, the human brain is essentially a biological computer calculating logical propositions. Now let's say we want a neuron that fires if either of its neighbors talk to it. This is the OR gate. Neuron 3 receives excitatory inputs from neuron 1 and 2. We drop the threshold theta to 1 instead of 2, and the result is that neuron 3 fires if neuron 2 or neuron 1 fires. And this is the equation for the OR gate. Either neuron 1 or neuron 2 fires at time t-1 for N3 to fire. So now let's use that inhibitory veto. We want a neuron that fires when neuron 1 fires unless neuron 2 tells it to shut up. This is the AND NOT gate. Neuron 1 is an excitatory input and neuron 2 is an inhibitory input. The threshold theta equals 1. The result is that neuron 3 fires if neuron 1 fires and neuron 2 does not fire. So this is the equation for the AND NOT gate. Neuron 1 must fire and neuron 2 must not fire at time t-1 for N3 to fire. Now let's talk about the limits of feed-forward nets, known as Theorem 3 in the paper. So what can these simple forward-feeding circuits do? The authors proved that a network without any loops, they call them nets without circles, can only compute logical expressions that evaluate to false when all their inputs are false. Think about it. If the network is completely silent, meaning no sensory input is coming in, a simple feed-forward net cannot spontaneously generate a signal out of nowhere. Let's discuss a real example, the heat from cold illusion. The authors modeled a real biological phenomenon. If you hold a cold object to your skin for a split second, you actually feel a brief flash of heat. If you hold it there longer, you only feel cold. Now, I want to pause to make a comment on this. The example presented here captures a real phenomenon known as paradoxical heat sensation. Warmth from cooling can occur in healthy people under certain experimental conditions, but it's not a standard response. I tried to replicate it, but it didn't seem to work out for me, so give it a try yourself and let me know if it worked for you in the comments. They modeled this with 4 neurons. N1 is the heat receptor, N2 is the cold receptor, N3 is the brain sensation of heat. There's also an N4, which is the brain sensation of cold. However, for now, I'm omitting N4 because it's irrelevant to the heat from cold illusion phenomenon. They wired up a network where the equation for feeling heat, N3, looked like this. What this represents is that you feel heat right now if the actual heat receptor fired 1 time step ago, or if the cold receptor fired 3 time steps ago, but stopped firing 2 time steps ago. The network structure literally creates the illusion of feeling heat from a transient cold signal. It proved that human perception is dictated by the wiring of our logic gates, not just a direct copy of the outside world. Now let's talk about the equivalence theorems. Computation matters more than mechanism. One of the paper's deepest ideas is that different biological mechanisms can produce the same computation. McCulloch and Pitts called these cases equivalent. For example, suppose inhibition is not an absolute veto, but only raises a neuron's threshold. They proved that this change does not alter what the network can compute, because an equivalent network can be built under either assumption. And this is stated as Theorem 4 in the paper. They make the same point about summation. A network that adds signals over time can be replaced by one that adds signals across multiple inputs with the same logical effect. And this is Theorem 6. The big lesson is that the messy biological details and the abstract computation are not identical. Different physical systems can implement the same logical structure. Nets with circles and the birth of memory. Finally, they turned to networks with loops, which they called nets with circles. In these networks, activity can re-enter the circuit and continue reverberating over an indefinite time. That makes the mathematics much harder because the outputs may depend on events in the arbitrarily remote past. The key conceptual point is that loops let the network carry information forward through time. The present state can depend on its earlier states. In modern language, that is the basic idea behind treating recurrence as a form of memory, and it's closely related to how later AI systems process sequences over time. If we step out of 1943 and look at this paper from the standpoint of modern machine learning and neurophysiology, some ideas held up remarkably well, while others did not. Computation. McCulloch and Pitts were right that the networks of simple units can compute complex functions. The basic idea still sits underneath modern neural networks. Implementation independence. Their equivalence theorems show that different biological mechanisms can realize the same computation. That is a major idea in both AI and neuroscience. Function and mechanism are related, but they are not identical. Recurrence and memory. They were also right that feedback loops make present activity depend on past activity. Now for what did not hold up. Real neurons are not binary logic gates. The McCulloch-Pitts neuron is a hard threshold device. It either fires or it does not. Real biological neurons are much richer, and their dendrites perform important nonlinear computations. Inhibition is not an absolute veto. That assumption made the mathematics clean, but real inhibition is much more flexible. Learning is too primitive. Their model is mostly fixed in structure. Modern AI depends on changing weights continuously through optimization, and real brains change through many forms of plasticity that are far more complex than simply adding a new connection. So the bottom line is, though McCulloch and Pitts did not give us modern deep learning, they did give us the artificial neuron and the idea that neural activity can be studied as computation.